I'd like to solve some problems where we're expanding and simplifying algebraic expressions. For example, we might be faced with a calculation where we have to multiply out two brackets, each of which contains a number of terms that are being added together. For example, something like this. And the idea is to systematically go through each of these terms and multiply them by each of these. So that, for example, because I have three choices of terms here and three choices of terms here, I expect to get 9 terms in total. I'll start with the x squared and I'll multiply through each of these three terms. For example, x squared times x squared. Well, what does x squared really mean? This is just an abbreviation for x times x. And so is this. So when I multiply them together, I really have x times x times x times x. And pretty soon that becomes unwieldy. Rather, it's better to have an abbreviated notation where we keep track of how many x's are being multiplied together in the exponent. So x squared times x squared, I'm going to write as x to the 4. And x squared times minus 2x, well, a good idea is to first of all figure out the overall coefficient of the product you've just determined. So negative 2 is the coefficient, and then I determine how many x's are being multiplied together, and there's 3 of them, so x times x, abbreviated as x cubed. X squared times 5, 5x squared. Now I'm done with this x squared term, and now I turn to the x and I do exactly the same thing. X times x squared is x cubed. X times negative 2x, the coefficient is negative 2. X times 5, I've got plus 5x. And so I've done 6 of the 9 terms. Sometimes the length of your page horizontally means that you have to kind of come down to the next line to write what the remaining terms you got to deal with. Usually people indent just a little bit. So for example, 1 times x squared, I'll write that as x squared. 1 times negative 2x. In fact, multiplying by 1 is easy. Those are our 9 terms, and we're done the expanding part of this problem. And now we're in the second stage of simplifying, which means we've got to collect terms that are of the same kind or of the same form. So for example, I look for x to the 4 elsewhere in my 9 terms that I've generated so far. There isn't another such case, so x to the 4 is the first thing I write down. And now I'm being systematic. I drop the exponent by 1. I don't write x squared stuff and then numbers and then back up to x cubed. More chances of making mistakes that way. So I turn to x cubed and I say, well, there's negative 2 of them here. And there's a plus 1 here, right? The default assumption is that if you don't write a number here, there's a number 1 there. So negative 2 plus 1 is negative 1. So that's minus x cubed. I turn now to the x squareds. There's 5 of them here, negative 2 of them here, another 1 there. So 5 minus 2 is 3, plus 1 is 4, so I've got 4x squared. Now the x's, 5x minus 2x, that's 3x, and then numbers, 5. Okay, and there's nothing more I can do. I can't add 4x squared to minus x cubed and somehow get something nicer. This is the nicest thing I can get. Okay? So that's a first example, and you can see that once you've done a few of these, there really is no other mystery to it. I mean, it's simply this process of expanding out to get all the terms you need and then collecting the terms that are of the same form. So let me do another example of a slightly different kind. Maybe a case where we're not multiplying, but actually we've got a fraction going on, some numerator, some denominator that involves x's. For example, 2x plus 1, all divided by, let's say, x minus 2 over x. And the idea is here, can we write this in a nicer way, cleaner, shorter, easier to understand? So what powers do I have when I've got a fraction? Like what kind of tools do I have to manipulate this expression and to know that I haven't changed its value? Whatever number this is, if I multiplied it by the number 1, it's not going to change its size. The interesting thing is, though, that you can express the number 1 in a bunch of ways. For example, 1 does equal 2 divided by 2. It's an unusual way to write it, but it can be a useful way to write it depending on the context you're in. Maybe I'd like to multiply this expression on the top and this expression on the bottom by the same quantity that would somehow make this look cleaner or nicer. What's the ugliest thing going on around here? It's that in the denominator itself I have a fraction of its own, 2 over x, and maybe I don't like that. So how could I quote unquote get rid of that? If I were to multiply the entire denominator by x, then yeah, this x would become x squared, but this term would become nicer. It would just be negative 2. Now I can't just unilaterally multiply the denominator by x, because then I would be changing the size of this. But I can multiply by x divided by x, and that's what I'll do. So I put a little dot there to indicate multiplication. Put an x on top here. And then now I realize, look, this kind of looks like maybe it's just the 1 multiplying the x. So just to cover my tracks, I like to put brackets around it so it's super clear that this x multiplies everything on top, and this x multiplies everything on the bottom. So what happens when I do that? X times 2x, 2x squared. X times 1 plus x. X times x, x squared. X times negative 2 over x. So I guess I could write here temporarily minus 2x divided by x, but x over x is 1. So really I can just write minus 2 here. There's nothing else I can do to make this look nicer, so this is the end of this question. What if I had a situation where I had 2 of these fractions and I wanted to add them together? That's the last of the examples I want to do here. We could have, for example, x plus 1 over, I don't know, x minus 2. And then let's say I'm subtracting x plus 5 over, let's say, x plus 2. Okay? How am I going to make progress on this? Well, the problem with adding or subtracting fractions is that you have to ensure that they have the same denominator. When you do have the same denominator, adding fractions is easy. So for example, if I have 3/7 of something and I add another 2/7 of the same thing, then in total I have 5/7 of that thing. Adding fractions is easy when you have the same denominator. You simply add the numerators. I'd like to engineer a situation where both of these fractions have the same denominator. They don't right now. This is a denominator of x minus 2. This is a denominator of x plus 2. Those are different numbers. So what can I do? Same trick that I used last time. I should multiply this fraction by some quantity over some quantity, the same quantity, and multiply this fraction by some quantity over some quantity, the same quantity. And as a result of those multiplications, I'm going to have a situation where this guy's denominator and this guy's denominator are the same. So the first time you see this, it's surprising, but after you see it once, you realize, oh, that's why it works. I'd like to multiply this fraction by x plus 2 divided by x plus 2, and this was a clever choice because look, this x plus 2 is exactly the same as this x plus 2. That's why I chose it. Now this denominator is x plus 2 times x minus 2. This denominator is still only x plus 2. If only it had another x minus 2 factor, then indeed it would be the same as this denominator. I can make that happen. I can multiply the bottom by x minus 2 as long as I make sure I multiply the top by the same thing. That way I know I haven't changed the size of this fraction. I've just multiplied it by the number 1 written in a slightly unusual way. Again, whenever I'm multiplying sums of things times sums of things, I put brackets to remind myself, hey, I have to distribute this x and this 5 over both of the things it's multiplying. Now I'm set up to proceed. I have the same denominator, so why don't I actually just write that denominator right away? X plus 2 times x minus 2. And on top, I multiply out this term, I multiply out this term, I make sure there's a minus sign that's attached in front of this whole thing. So I'll do this relatively quickly compared to earlier. X times x, x squared. 2 times x, 2x. 1 times x is 1x. So I've got 2x plus x. 2 times 1 is 2. This is the result of multiplying these two expressions. Now I put a big minus sign and I open up brackets. Because inside these brackets is going to be contained the result of multiplying x plus 5 times x minus 2. And yeah, that looks like x squared plus 5x minus 2x minus 10. Okay? So the last stage is simply to combine the tops by collecting terms. For example, x squared minus x squared is 0. 2x plus x is 3x, and then I'm subtracting 5x minus 2x. That's also 3x. This is 2 minus 10, that's going to be 12. What I'm trying to show here is that you don't have to get bogged down doing everything in order. You can select the terms you want and collect them immediately. So x squared minus x squared, that is 0. 3x here minus this. Okay, the 5x minus the 2x, that is 3x. And now I've got the 2 and the minus negative 10 to deal with. With the same denominator that I'm not improving. I'm leaving it as it is. And now we're done pretty much. This is 0. 2 minus negative 10, that's 12. And we're finished. Even though there's a temptation to multiply out the denominator. I mean, there's a bunch of multiplying out going on. How come we don't multiply this out? The reason you never do is because this is more information than if you multiplied it out. I can look at this immediately and realize that were x equal to the number negative 2, this denominator would be a 0, and that's a problem. Division by 0 is impossible to achieve, okay? But if I multiplied it out, I wouldn't be able to see that.